This video will show you some applications of quadratic equations. Some of these will involve geometric formulas like the Pythagorean theorem or the area formulas, and then the last one will involve a model that's actually given to you. Example 1 is a fire truck parks 30 feet from a burning apartment building. The ladder must reach the fourth floor of a building that is 36 feet above the ground. Given that the ladder is raised from the top of the fire truck, which is 12 feet above the ground, how far must the ladder be extended? And so we have to understand here that the fire truck, building, and ladder make a right triangle. And so we're going to use the Pythagorean theorem, which is a squared plus b squared equals c squared. And our legs are the distance from the building and the height up the building that the ladder needs to reach. We are told that the distance from the building is 30 feet, so we'll let A be 30. A and B are interchangeable. Then the distance from the fire truck to the top of the ladder is what the other leg needs to represent. Since we're 12 feet above the ground is where the ladder actually starts coming up, and we need to go 36 feet up, we really only need to go up 36 minus 12, or 24 feet. And then how far must the ladder be extended? That we don't know, so that is our unknown, or x. So squaring 30 is 900. 24 squared is 576, and that's equal to x squared. Adding 900 and 576 gives us 1476 equals x squared. We solve this by applying the square root property, which states that x is plus or minus the square root of 1476. And because this is an application, we just want to approximate that value in our calculator, and we'll get approximately 38.4. Now, because we are looking at an application and x represents the distance that the ladder must be extended, the negative value doesn't make sense. So the correct value would be that the ladder has to be extended 38.4 feet. Example 2 is Jensen plans to pour concrete in a uniform width around his rectangular pool to form a walkway. If his pool measures 20 feet by 50 feet, and he has enough concrete to cover 800 square feet, how wide can the walkway be? So this is getting into the area formula, in which we know area of a rectangle is length times width. The issue here is that the concrete will only cover the width of the rectangle, right? It won't cover the actual pool. And so the way we have to do this problem is we find what's the huge area, right? If we looked at the pool and the walkway, what is that combined area? But then we subtract out the area of the pool, and that leaves just the area of the walkway. So our equation will come from the area of the total minus the area of the pool must equal the concrete that we have to cover, which is 800 square feet. So the area of the total concrete and pool is, notice that if we are extending it by a uniform width, that means that our width of the pool, or width of the walkway rather, is going to be x. And if we're extending it on every side by that value, then we are actually increasing the width of the pool by 2x, and we're also increasing the length of the pool by 2x, because it's x on each side. So the total combined length and width of the pool and concrete path would be calculated as 20 plus 2x times 50 plus 2x. And now we're going to subtract off the area of the pool, which is just the 20 times 50. And set that equal to 800. So we multiply this out. 20 times 50 is 1,000 plus 40x plus 100x plus 4x squared minus 1,000 is equal to 800. Combining like terms, we get this as 4x squared plus 140x. Note that the 1,000s add to 0. And now we need to set it equal to 0, so we can also at the same time subtract 800 from each side, and that would be equal to 0. And then we can find a common factor. A common factor of 4 exists, so if we divide each side by the value 4, we get the equation x squared plus 35x minus 200 equals 0. Now we can solve this equation by factoring, or if you don't like factoring, you could use the quadratic formula, but I think it does factor. We need to find the factors of 200, whose difference is 35. And so if we think about the factors of 200, we have 1 in 200, 2 in 100, 3 doesn't go into it, 4 and 50, 5 and 40, and actually that's a combination we need right there. So we put in x and x for the factors of x squared, 5 and 40. We know the signs have to be different, with the larger factor being positive, so a plus on the 40, minus on the 5. So now that we have it factored, we have to set each of those factors to 0. So x minus 5 equals 0, or x plus 40 equals 0. And so our solutions are either x is equal to 5 or x equals negative 40. But because we're trying to figure out the width of a walkway, the negative 40 does not make sense in the context of this problem, so the walkway would have to be 5 feet for these dimensions to be satisfied. Another example here is that the number of pieces of mail delivered by the United States Post Office X years after 1980 can be approximated by m equals negative 0.141x squared plus 5.2126x plus 52.109, where m is in billions, and we want to determine when there will be approximately 25 billion pieces of mail delivered. And so this is a situation in that we are actually given a model and we are given a value that we want that to equal. And so in this problem, we want to set m, our model, equal to the number of pieces of mail, 25 billion. So our equation is negative 0.141x squared plus 5.2126x plus 52.109 equals 25. To solve this quadratic equation, we have to get it in standard form. So we first want to subtract 25 from each side to set it equal to 0. And when we do, we want to combine like terms, so that gives us negative 0.141x squared plus 5.2126x plus 27.109 equals 0. And then, just so that we don't have decimals in the problem, we can get rid of the decimals by multiplying through by a power of 10. In this case, we're going to multiply through by 1,000 and actually negative 1,000 so that we can get rid of the negative in the leading coefficient. Now, this won't actually get rid of all of the decimals. To get rid of the 4 decimal places in the middle term, we would have to do 10,000, but that's going to make our numbers pretty large, which they're already kind of unruly, but that's why we have a calculator to deal with that. So multiplying by negative 1,000, we're going to get a positive 141x squared, then minus 5212.6x minus 27109 equals 0. And at this point, we can use a quadratic formula to solve this equation. So we have x is equal to the opposite of b. So remember our a, b, and c. So the opposite of b would be the opposite of negative 5,212.6 plus or minus the square root of b squared, which is negative 5212.6 squared, minus 4 times a, which is 141, times c is negative 27,109. And that is all divided by 2 times a, or 2 times 141. And at this point, we can substitute into the calculator, and we'll get the opposite of negative 5212.6 is positive 5212.6 plus or minus the square root. And if you simplify that expression inside, you're going to get this really horrible number. It's 424,606,74.76. And that's all divided by 282. And so approximating these values on the calculator, we will get that x is either approximately 41.6 or x is approximately negative 4.6. And again, because this is an application, the negative doesn't really make sense in the context, so we will say that there will be approximately 25 billion pieces of mail delivered in 41.6 years after 1980. And so that's going to take us to the year about 2021.